Hello, everyone. We are the team studying the effect of a dihedral angle on the aerodynamic performance of a finite wing. This group includes myself, Taylor Converse, Shane Benziger, Jeffrey Clark, Owen McGuire, and Anthony Perazon.
The objective of the following test was to analyze how the lift and drag of an aircraft are affected by a dihedral angle. 3 models were created using SolidWorks and printed using a 3D resin printer to ensure durability during wind tunnel testing. One model featured a dihedral angle of 0 degrees, while the other 2 had an angle of 3 and 6 degrees. Each model was tested at an angle of attack ranging from 0 to 14 with increments of 2 degrees. Overall, the key question this test attempts to answer is how can the manipulation of the dihedral angle of a wing improve its overall efficiency? One of the most important characteristics of flight is stability, which is directly related to the dihedral angle on the wing. However, excessive dihedral angles can result in a sharp increase in drag, reduced stability, increased turbulence, and a Dutch roll/corkscrew motion. Since the dihedral angles in this test are small, the effect they have on lift and drag is minuscule. Prior study in the aeronautical engineering industry has focused on flow over a wing with varying dihedral angles. This study will focus on a fixed dihedral angle on a wing throughout the duration of flight. The results from testing the effects on the dihedral angle can be applied to improve economic, social, and environmental aspects of society. Most importantly, they will be applied to improve the efficiency and performance of an aircraft. An increase in efficiency leads to reduced fuel consumption, more smooth flights, and lower operating costs. Lower operating costs translate directly to consumers, allowing them to save money on flight prices. Lower fuel consumption reduces the fuel emissions, further reducing the negative impact aircraft could have on the environment. Before testing was conducted, theoretical analysis was conducted using the lifting surface theory. MATLAB was used to evaluate this analysis because of difficulty with ANSYS. The lift over the wing was calculated using equation 1 as shown, where rho infinity is the air density at sea level, v infinity is the wind tunnel velocity, s is the planform area, and cl is the coefficient of lift. To calculate the lift coefficient was calculated using equation 2, where alpha is the angle of attack, a is the three-dimensional lift curve slope, and alpha at L equals 0 is where both angle of attack and lift is equal to 0 because the airfoil is symmetric. Equation 3 was then used to correct the lift curve slope for an incompressible, low aspect ratio finite wing, where E is the Oswald efficiency factor, AR is the aspect ratio of the wing, and A naught is the two-dimensional lift curve slope, defined by equation 4. Using these equations, the lift acting on the wing was approximated to reach a maximum value of 6.73 newtons. Drag cannot be approximated accurately due to the lack of data for each model.
So the following plan on this slide outlines our plan for our experimental process. So we first set up our first model, which was our 0-degree dihedral, and the wind tunnel ensured it's secure inside the mounted portion. We turned on the wind tunnel and set the speed for 36 meters per second, and this was held constant through all of our experiments. We calibrated the LabVIEW processor as well as the pyramidal force balance using the hanging weight method. We set the angle of attack to 0 degrees as our starting mark. We ran the test measuring the lift and drag voltages from LabVIEW from the force balance. We recorded the data from LabVIEW and entered it into Excel after obtaining all of our voltages. We increased the angle of attack by 2 degrees, going up to an angle of attack of 14 degrees. We repeated steps 5 through 7 until this was achieved. We removed the 0-degree dihedral model from the wind tunnel, and we set up the 3-degree dihedral model and repeated previous steps 2 through 8, achieving the same thing for the 6-degree dihedral model as well. So for our experimental setup, if you look to the right on our second image, we have our approximate positions for our test setup. We have our model mounted into the test section of the wind tunnel where we have the pyramidal force balance directly underneath it, flow going across the model. If you look at our data collection sequence, it starts with the wind tunnel in which it shoots air at our models where we obtain forces for lift and drag that are present on the model. From that, the force balance picks up these forces and are processed in the transducer phase by our load cells. Then they go into conditioning, where they are received as voltages in our LabVIEW software. So that travels through our DAT card, which is plugged into our computer and is read through the software, in which we observe the changes in real time. This data is collected and processed into Excel and furthermore into MATLAB, where we get more accurate and visually pleasing graphs. And then we are able to elaborate on these results and analyze them with our known knowledge of aerodynamic theory. And below are also important variables and parameters, which are elaborated before in the theoretical results section, such as coefficient of lift, angle of attack, Oswald efficiency factor, and so on. So for our test equipment, it consisted of the following. We were in need of an Aerolab open circuit wind tunnel, a pyramidal force balance, force transducers to pick up the forces, which we used bridge thin beam load cells. We needed a signal conditioning board, which converts the transducer response to an output voltage in which we can read. We needed a DAT card and a CB68 interface. We needed a computer with LabVIEW software to extract the necessary voltage into data that we can use. And then for processing software, we needed Microsoft Excel and MATLAB. An important thing to note is all of these softwares were already in our possession, owned by the university, so we no longer needed to acquire other things at an additional cost, which saved money and also made our project feasible.
So taking a look at the group schedule, a Gantt chart was created during the planning part of the project. This schedule presents two different plans in the case that the group encounters any roadblocks. With our project coming to an end, the Gantt chart can be reevaluated for the meeting of any deadlines. And most of the project was completed ahead of time. In specific, the 3D printing of models was pushed back to March 29th through April 6th. With that in mind, testing was then moved up to April 6th. However, with issues in our data, we retested on April 18th, which put us exactly on schedule. Calculations were then performed on the data on April 19th, putting us ahead of schedule once again. We initially were not informed of the viscosity lab. However, that was added into the schedule to be completed on April 22nd, April 24th. The final paper was written on April 28th, and the presentation was completed on May 2nd, well ahead of schedule. In terms of the group's budget for this experiment, the group took into account all equipment required throughout the experiment. In reality, the group did not need to purchase this equipment due to Clarkson already owning it. Therefore, the only real cost the group endured was the mounting hardware, which was roughly around $6. A basic risk assessment can be conducted on the wind tunnel where flying objects, loose objects, heavy moving parts, and most importantly, noise are evaluated. Earplugs could be worn to prevent ear damage, along with avoiding the inlet and exit of the wind tunnel to prevent any other injuries.
The group had to first create calibration curves to fit our data to. We did this by loading the force balance with known masses and recording the millivoltage output. Then we could fit our data to the curve. LabVIEW outputs a millivoltage, which we could then convert to a Newton based on the calibration curve. Once we collected our data, we noticed a strange spike in the lift figure, white figure at the top. The 0-degree dihedral model has a strange spike in the lift data at 12 degrees. This would suggest a premature stall. So we retested and found the same strange spike again. Otherwise, our data follows the expected results from aerodynamic theory. Since dihedral angles are for stability and control and not increased aerodynamic performance, it follows that the difference in each of the curves is on the order of millinewtons. There is not a significant aerodynamic performance increase between the dihedral angles. Furthermore, the gradual increase in the drag and lift as the models approach theoretical stall angles. It should be noticed that we did not complete our experiment at or after predicted stall angles. Design stage uncertainty was calculated for this experiment. Instrument and zero-order uncertainties were found from spec sheets for the instruments used in the sensor transducers and signal conditioning stages. Resolution error is 1/2 the resolution of the LabVIEW measurement, which is 0.001 millivolts. The sensor transducer stage had a 0.25% error, and the signal conditioning stage has a 0.05% error. Using the RSS method, uncertainty was calculated for each stage, and then the RSS method is used to find the total design stage uncertainty for the experiment. Overall, the design stage uncertainty for our experiment was approximately 0.27%. We find this acceptable since usually under 10% is considered acceptable. We are confident in the results of our data based on the low uncertainty percentage.
So from the graphs developed relating the lift and drag force to angle of attack, the changes of force compared to each dihedral model are only within hundredths to thousandths of a Newton, indicating that the changes in aerodynamic force with an increase in dihedral angle are minuscule. This validates the theory discussed at the beginning of our presentation. However, odd trends observed in the 0-degree dihedral were found in 2 separate experimental attempts, indicating that the behavior was not due to a single experimental error. This abnormal behavior could be due to the manual adjustment of the angle of attack of each model, in which the team actually reached stall angle of the wing prematurely, leading to the maximum lift shown in the graph. Some possible sources of error within our experiment include having to manually change the angle of attack and use our judgment in determining the proper angle. Additionally, the uncertainty of the load cells used, of about 0.25%, could have introduced some error, but it's likely not as much as other sources, including printing limitations leading to unideal model wingspans, and the body of the model having a blunt face. To improve our experimental setup, we could have developed a more conventional streamlined fuselage to limit unrealistic drag characteristics on the body, and increase the wingspan of each model to the desired length in order to ensure more accurate lift results. Additionally, a more robust method of manipulating the angle of attack of the wing model can be used, as well as a more accurate method of reading voltage output data without excessive noise. First, we would like to thank Matthew Turner and his continued guidance throughout our study, especially in the development of the voltage output acquisition system and calibration proceedings. We would also like to thank Dr. Carl Hoover for his continued support in our project as well, including his constructive feedback and continued observations of our progress to keep us on track to complete this study in a timely manner. We would also like to thank the Dorf Makerspace for processing and printing our wing models in a timely manner. Thank you. And here are our references.